right, let's just resume our class. Okay, so we just in the previous lecture we talked about deep gradient compression and see how it's reducing the communication as well as like actually marginally improve the accuracy. But the DGC method actually there's still room for improvement. So if you think about it, so the sparse gradient when they are got communicated to the parameter server, or like when you are doing the range reduce, the sparse gradient actually got denser and denser. Why? If you look at the example over here, if you can just look at the example over here. So we have a four workers. So if the first worker 0 has a weight gradient as like 11100 and all zeros over there. Okay. But the problem is that like the other worker, their top K gradient is not necessarily the same top K gradient from here. Okay. So the top K from here is not the top K gradient from this worker, which is not the top K gradient from this worker. So all those gradients, the top gradients are different. Does that make sense? Therefore, when you are trying to do a range reduce of them, you need to add all these gradients together, right? And that eventually makes all these gradients denser and denser. And after multiple rounds of communication, all the gradients are coming back again. Does that make sense? Okay. So therefore we need to do something to fix this gradient got denser and the denser problem. Okay. So one idea is that how about let's share the same sparsity pattern. What does that mean? Well, here, let's say like if we give the index to this, like 1, 2, 3, 4, this is totally 10 gradients. Okay, so this is 6, 7, and 8. Those are 6, 7, 8. Those gradients are the top K, top 3, right? And these are, these two are the top 2, top 3, and top 2. Okay, and they are all in different indexes. So when you are combining them together, they become a not so sparse gradient matrix. Okay. One way is that like we give up the top K criteria. Okay, so we can give up the top K gradient. Let's say like we kind of, if we can get some kind of consensus, let's say roughly top K, but also like they should be in this exactly same position. Does that make sense? So if like we say, well, let's say like for 1, this is 0, 0, 0, they may not be top K, but they are still quite big. Then like I'm going to use this and accumulate, keep these in the local. Does that make sense? So in this way, we can make sure like even after multiple rounds of all reduce, all the gradient we are sending is still sparse. Okay, does that make sense? But do you guys like see any problem with this solution? Do you guys see any problem with this solution? Like, maintain the same sparsity. You guys don't see any problem? It's okay if we just, maintain the same pattern. Let's say like just index 6, 7, 8, and every worker always just communicate the 6, 7, 8. Would that be a problem? So what is the drawback of this method? Well, if everyone just keeps like 678, well, every time we just communicate 678, um, first, as for the correctness, that's fine because these weights, these top K weights may not be sent first, but eventually, like, because eventually we are going to rotate across all these indices, right? Eventually, they are going to be, they are just saying like converging at different speed. Okay, the main overhead for this is how do you? So every time you need like all these workers, they need to find a consensus to say like, they must be high enough, but also like maintain the same pattern, right? So you need the to extra communication to find the common gradients that's big enough, but also the same position. Does that make sense? One way, of course, is every time I'm just sending, I'm just sending all those gradients, broadcasting and find the common but big enough. But that beats the whole purpose of specification because the communication overhead is just too big, right? Right. So people like propose different optimization techniques. For example, like, let's say like we are dividing all these gradients into blocks. Let's say like these are just into two half. Okay, like I'm just going to dividing this gradient into two blocks, the top block and the bottom block. Okay, and then like I'm going to like use a binary vector to represent these two block. And every time, let's say like which block is bigger, and I'm just going to send a vector like if both of them are greater than like for example a threshold, I'm going to send a 1 1. I'm going to send like if this one, for example, I'm going to send a 0 1. Okay, so I'm using a vector to kind of roughly estimate which blocks are greater than a threshold, for example. And using that vector, the communication overhead is reduced, right? But we still need like this extra round of communication to do this. Okay, and then based on this vector, we can do a binary operation to kind of find the common blocks that's higher than the threshold, but also like they are common. Does that make sense? Okay, so that's one way to do this. So we can do this, but you need to introduce like this extra synchronous agreement overhead. Okay, there's an extra communication overhead for agreements to reach the agreement. Another way is that possible way to prune is that well, so every time when we communicate, like let's say like after 3 rounds, we start to make the gradient dense again, right? Another idea is that oh, once it becomes dense, for example, like the number of gradients is greater than how many percent of the whole vector, then I'm just going to do another round of pruning. Okay, so this, for example, I have only 3 gradients, but this one has 5, there's a 4, 6, and 5. Okay, then I'm going to, once I reach to this stage, I'm going to do another round of pruning, and I'm going to discard some of it. And now they are sparse again. Does that make sense? But what's the problem with this solution? If in the middle, like now I'm going to discard the smallest 2 number. Okay, what's the problem? Can we do that? Well, if you just suddenly just discard like you only keep the top K and throw away like the other 2 gradients, what's the problem? Those gradients just gone, right? And they were never going to be updated to the weight. right? So you are going to see an accuracy drop, but will that be a big problem? You see my problem? So if you just throw them away, then like all those gradients I calculate just gone, right? Even though like you are maintaining the communication efficiency, but my gradient just gone. But the problem actually is much it's better than we thought actually. So it's actually quite safe to just throw them away. Why? So people find out like if I just throw them away, just keep the top K, and those gradients just got thrown away, but the final accuracy actually did not drop too much. Why? Can anyone think of the reason why actually the accuracy is not affected too much? Because when I was reading, the paper, I was thinking to myself, that can't be because, that's going to be affect the accuracy a lot. But actually, like, it turns out not. See who can guess the reason. So the reason is that, so even though like, I'm going to discard, all those gradients. So basically what that means is that in this round of update, those two weights are not updated at all, right? So in this round of update, the weights are not updated to my model. So then in the next, think about it, in the next iteration, basically at this stage, my model becomes a worse stage at this stage in this iteration. But then when you keep training the model, the ground truth you learned from the data is going to keep pushing because your weight was not updated, right? But now when you are learning from the new data, all those remaining data is find out your weight actually is not as good as it should be. Then the new data will keep pushing your weight towards the correct direction. So in the next round of operation, in the next round of training with a new batch of the data, eventually all those discarded gradients is going to catch up. Does that make sense? So that's the reason why they can do that. But nonetheless, these two methods are kind of like just small fix for the DGC, and both of them kind of give you a little bit extra overhead or like a little bit accuracy sacrifice, right? So this power SGD is another way trying to fix that problem. Okay, instead of like this another way of doing sparsity to reduce the gradient communication. So instead of using simple top K pruning, this Power SGD is trying to do this row rank factorization. What that means is that we all know that if you are like LoRa technique like LoRa, what that means that basically for a matrix we can factorize this matrix into two low rank vector. Okay, so for example, like let's say like this matrix, this 3x4 matrix, it can be factorized into 3x1, 1x4. Okay, and then like this matrix essentially equals to the outer product of these two, not inner product, but the outer product. What that means is that like U1 times V1, U1 times V2, U1 times V3, U1 times V4. Okay, get one row, second row, third row. Okay, and we can factorize a original matrix into two vectors like this, and this U times the V transpose is going to get you it's not going to be exactly the same, but give you a very close approximation of the original matrix. That's the whole point of low rank approximation. Okay, so we good with the math here? Okay, so that's the point of the low rank. So now the problem basically says, then for this gradient matrix, all the gradients we are sending, we are going to factorize them into two low rank vectors. Okay, and then like every time when we are sending the whole, originally we need to send in the whole matrix, right? Now we only need to send in two low rank vector. Does that make sense? So let's see. But also there's a catch. So now, like if let's say like we have two nodes, 1 and 2. They have gradient G1 and the G2. Okay. And then we are factorize G1 into P1 and Q1, factorize G2 to P2 and the Q2. Okay. Now each of them has two low rank vector instead of the whole matrix. Okay. And when they are sending, G1 is sending P1 to Q1 over, G2 is sending P2 and the Q2 over. Okay. So we're just sending like low rank because that reduces the communication. But then like when you are trying to recover the gradient, originally, what we need to do is basically, without all these stuff, like what we really need to accumulate is G1 plus G2, right? So that's the thing that we want to recover, G1 plus G2. Right? Without the factorization, if we're just sending over the whole gradient over, when we are doing all the reduce, eventually we need to have G1 plus G2, right? Make sense? But now we are sending P1, Q1, P2, Q2. What we can do is that like we can add in P1 and P2 times Q1 and plus Q1 and Q2, right? But this does not equal to G1 plus G2, right? Why? If you expand this equation, what we have is this: P1 plus P2 times Q1 plus Q2. You got this P1 Q1, P2 Q2, okay? Plus all these terms, these cross terms. The first two terms equals to G1 and the G2, but we have two extra cross terms now. Does that make sense? Now it's a little bit off. It's we are no longer recover the G1 plus G2 with this factorization, right? Does that make sense? So see, it's always like when we are thinking about a problem, when thinking about a solution, it's always like this. We came up with the solution, it's not working as we intended. So we need to keep finding fix the solution to find a solution that solves the problem. So then like we need to eliminate these two cross terms basically. Okay, in order to do the factorization. So the trick is this. The trick is this. So the trick is that we are not sending P1 Q1 and the P2 Q2 simultaneously. Okay, what we do is that for G1 we are fixing the Q vector. So we keep a Q that's the same Q. So both node 1 and node 2 is going to have a same Q kept in their own memory. Okay, and then like G1 and G2 is going to factorize into Q times P1 and Q times P2. Does that make sense? Okay, so what we do is that each node uses a shared Q. Okay, so G1, P1, G2, P2, but Q is always the same. So therefore, these two nodes, they are only sending the P's over, and they share the same Q. If you do that, then because the Q is the same, then you're just adding the P together, and that's going to give you the G. Okay, so by doing this, the P all you can by accumulating, these GIs. By doing this, we are only sending the P, and accumulate them all together. So we are kind of getting a P all that represents the left side of the global gradient. Okay. So once you have the P all, and then like because every node has a P all, right? And then like we calculated the QI inside each node, and then broadcast the QI. Now because everyone is sharing the same P all, and they have their own QI, and then broadcast the QI, then you can have the Q all, which is the other side of the global gradient. So by doing this two-step, you calculate the P all and the Q all, and that gives you the accumulation of the G all. Okay, so by doing this two-step, we can eventually got the G all. So they evaluate this low rank factorization method. This backhand is intended for CPU training. This is for like NVLink GPU training. So this is kind of like cluster of CPUs, cluster of GPUs. Okay. The SGD is the rank 2 is the one that the factorization the low rank gradient. So you can see the blue line give you the best speed up in both cases. Okay. Comparison of gradient pruning method. The gradient specification. And then we talk about the DGC, which you have this momentum correction, you have this gradient, you have the warming up the training as well as the specification. Okay, and then we talked about the DGC also, like when you do more rounds, you are going to make the gradient dense again. So we can have some more optimizations, but this Power SGD is another doing this low rank vector factorization, matrix factorization instead of like pruning. Okay, so those are all different ways of trying to, doing the specification for the gradient transferring. Okay. So next, instead of like pruning, let's talk about the quantization. It's also quite interesting. So for quantization, for a 32-bit gradient, we quantize into 1 bit with a quantization error. Okay, so how it works is like this. So for the whole gradient, if it's greater than 0, then it's quantized to, into a binary stuff, and then like you have some this quantization arrow, and to also the quantization arrow is going to be kept in the local buffer. This one is doing this column-wise scaling factor. What that means is that for each column, we are having one scaling factor. So this one is mu1, mu2, mu3, and mu4. So so basically, the original gradient matrix becomes this code book. Each column we have one number, so we have a code book of 4 numbers. Does that make sense? And also, like each number, either depending on if it's positive or negative, becomes 1 and the zeros. Okay, so each gradient becomes a binary plus a code book. Okay, and then like plus the quantization arrow, and the quantization arrow is kept in the local worker and to keep communicating with the new gradient. So every time when you are transferring, we just need to transfer a binary matrix plus a small code book. Does that make sense? So in this way, you are trying to do so because we learned so many things about the quantization. So this should be quite straightforward. Another way, instead of doing the binary column-wise quantization, they also have this so-called threshold quantization. So they define a threshold of tau. So if it's greater than tau, it's or less than tau, and it's positive and the negative. If it's in the middle, it's 0. So the value tau need to be empirically chosen. Okay. So this way, basically, you are quantize this whole thing into a 2-bit number. Right. So positive, negative, and a 0. So you need like 2 bits to represent this whole table. Okay, and then like of course you have a arrow delta and kept in the local and keep accumulating. Current gradient is also a very interesting idea. So for these two, this is 1-bit SGD and this is a threshold quantization, like all these arrows need to be kept accumulating in the local worker, right? So this arrow needs to be keeping in the local worker. So it's accumulated with the new gradient, and the quantized arrow come back and accumulate with the new gradient and doing this over and over again. What that means is that we need to keep one copy of gradient and also one copy of the quantization arrow, right? So turn gradient is trying to fix that problem. And it's trying to eliminate the need for this quantization arrow. It does not need to keep another copy of this. What that is that we are quantized to GI to max G to 0, 1, -1 with the probability of this, such that the expectation of this quantized equals to GI. What does that mean? So let me give you an example. Let's say I have let me see if I have a good number example. Let's say I have a bunch of numbers, like I just randomly 1, 2, 3, 4, next 3, next 5, 6, 7, 8, 9. Okay. So if I have all these numbers in my gradient matrix, what I'm going to do is that first I'm going to find out the max G, which in this case it's 9, right? So then like I'm going to quantize this into all these GI, or I'm quantize the so basically if you are quantized GI divided by max G equals 0, 1, -1, basically you are quantized G into 0 and G and negative G. Right? In this case, the max G is 9. Right? Does that make sense? So basically now I'm quantizing all these numbers into either 0 or 9 or -9 with a probability. And what is the probability? The probability is like for 1 over 9. For this, it's 2 over 9. Okay, so what that means is that for this number, I use the probability, say 1 out of 9 times. If I see the number 1 out of 9 times is going to be quantized to 9, but 8 out of 9 times is quantized to 0. Okay, and for the number 9, basically says I'm always quantize this to 9. It's 9 out of 9 times. I'm going to quantize this number to 9. Okay, and this -5 is going to be 5 out of 9 times quantized to -9. Does that make sense? Okay, so therefore, for all these numbers, with a probability 1 out of the max number, with this probability to quantize either to 9 or 0 or -9. Okay, so you understand the idea, right? And by doing this, the expectation is that, well, if you train this model long enough, sometimes it got to 9, sometimes got 0, sometimes got to -9, right? And because it's the number follows the distribution, then if you are adding them together, let's say if we train this model like 9 times, okay, so only 1 times got to 9, and the rest of the 8 times got to let's say 0, right? And if you're adding the expected number of this value, it's 1. Because the first time is 0, 0, 0, 0, and the 9, right? So it's 0 times 1 plus 9 times 1 of 9. So this expectation actually equals to 1. Does that make sense? Okay, so that's the key idea behind this. Okay, so basically that's what I described. Like I'm finding the maximum absolute value of maximum G, and each one is mapped to a ternary value, -9, 0, or 9. Okay, if the value is G is large or close to the maximum, it has a high probability kept as this. Okay, if it's light, small probability be 0. And if it's like close to the -9, it's going to be high probability to be -9. Okay, and you end up with a very sparse low precision matrix. And the expectation is that after so many rounds, eventually that number is going to be 1 or the number. Okay, why does this matter? So even though a single quantized gradient is noisy or wrong, because it's very wrong, right? It's 1 becomes 9, it's very wrong. But if you're averaging them across 1,000 works or over 1,000 training steps, and when you're adding them together, the noise cancels out. The big picture. So instead of like the 1-bit SGD or the DGC, the turn grade is mathematically honest from the start. Doesn't push the model in the wrong direction. It just adds 0 mean noises. It's adding but all these noises adding together, it's the number that we're expecting. Okay. And then if you look at the equation, because we don't really need to keep the arrow because we're just accumulating across so many works and so many training steps, the number is going to be a number itself. So we needed this, we don't need this. Okay. So that's the key idea behind this no residual. Okay. So it operates on the fly. It doesn't need to accumulate the arrow because the randomness is the compensation. Over the time, the missed information is naturally recovered by the probabilistic nature of the next round of quantization. So that's the beauty of this randomized quantization. Okay. Right. So that's TernGrad. Okay, very interesting work. So then all these things we talked about, gradient pruning and the gradient quantization, they are trying to improve the bandwidth, right? So next I want to talk about this delayed gradient update, which is trying to fix the latency problem. Okay, so let's see what is the latency problem. So the bandwidth can, all these techniques trying to improve the bandwidth. But the problem of latency, actually, you can't really fix it because that's so far away, and that's even you travel by the speed of light, the speed of electricity is still so far, right? There's no way we can fix that. The bandwidth, we talk about the bandwidth. So we can compress the gradient, and you can always improve the hardware, right? So those are things that the bandwidth. But latency is hard. From US all the way to China, it's that far. From Boston to Shanghai to Boston, the speed of light still takes 162 milliseconds. Okay, that's the physical limit. There's nothing that we can do. So if you have really a distributed workers across the globe, then it will be very slow and they converge very slow. The training is going to be very slow. What do? We can still do something about it. Okay, so this is the ideal situation where the worker 1 and the 2, they are computing, communicating, right? But when we are introducing the latency, now the yellow part is the latency becomes bigger and bigger. Eventually, probably even bigger than the computation. Okay, and that significantly increases the latency and reduces the throughput, right? So what do we do? One thing is that while local updates and communication are performed sequentially, so for the workers in this stage, I have to finish until the communication to finish so I can start the next round of training, right? Nothing I can do about that, okay? But the idea here is that, well, if the communication latency is so far, it takes for other worker to send me the gradient. So what happening inside of the local worker? Like if I'm a worker, what's happening is that I already finished my own gradient calculation. My batch of data, I train it, I got my own gradient, right? But now I'm keep waiting for others to send me their copy of gradient so I can have the total gradient. That's the problem, right? So now what I do have is that I have a copy of the latest gradient, okay? But also I have a copy of all the gradient from other workers. Does that make sense? I have all the gradient from the previous iterations from other workers. And I have the latest gradient for the current iteration from myself. Does that make sense? Can I do something about it by using the newest gradient from myself, also the stale gradient I got from the previous iteration from other workers? Okay, if I do this, what will happen? Means that all the gradients are from other works are all stale, all the old gradients. Now only has a copy of my new gradient. If I just keep using that, can I still update the weight? I have a stale gradient from other works, but I have a latest gradient for myself. Can I use the mix and match and using the old and the new to update my weight? So that's kind of the idea, right? Let's see what will happen. Okay, if I do that, what will happen? What happens is that, for example, like ideally, like one sending to and that. In reality, is that when one is trying to sending to the worker, it takes multiple. The computation might already finish multiple iterations, and data eventually arrived. Okay, that's multiple iterations earlier. So that's a problem. So what we are trying is that, well, I'm going to update the weight with the latest gradient from myself, but the old gradient from other people. Okay, because this average G is this iteration minus D. That's delayed D steps. Okay, so I'm going to update it with this. Okay, so if we don't care about the accuracy, if we just look at the system, it improves because now the communication actually got hidden by this overlapping, right? So basically, what happens is that, well, when I'm done with the previous iteration, I can immediately start to do the updating with my own latest gradient. I don't need to wait for other people send to me, and only after a couple of iterations, like right here, like if I'm a worker at this stage, I'm going to update the weight using my latest gradient, and at that time, suddenly I got all the old gradient from other workers, right? Got delayed workers. I'm going to use that equation to update it. Okay, system-wise, we are totally hidden the communication overhead. Accurate-wise, it's going to be a disaster, right? Right. So at least like we are not as good as like using the latest. Okay. So system-wise, we're improving. Accuracy-wise, we are losing. Okay. So we need to do something about the stale gradient from other workers. Okay. But you understand, like system-wise, we are winning, right? Okay. So the problem is this: deal with the staleness. So what we can do is that what happens is this: directly applying, I just using my the weight to minus the gradient from these steps earlier, that's going to definitely hurt the performance. And that's the result. You can see that, well, without the correction, simply using, what is the, oh, that's the D is the step. So how many steps earlier? So you can see that, well, if I just using delay 5 steps without any correction directly applying this, the accuracy is 88. If like it's 20 steps, it's even older, right? Like even older. But if it's long enough that I have to do this, then accuracy is even worse. Okay. And this is like the accuracy like after some fixing, this gradient correction. So the gradient correction is doing this. What we did is this. Well, what I'm going to do is this. For my weight, I'm going to minus this gradient, okay? And in this gradient, what I do have is my newest gradient. This is my newest gradient, okay? This is my gradient. This is my gradient. That's this step earlier. And this is the gradient from all other workers. That's these steps earlier. So what that means is that, well, for this stale gradient from all other workers, I'm going to minus my gradient also from these steps earlier, because I have that, right? That's from myself, just these steps earlier. I'm going to minus that and plus my newest gradient. What does that mean? What that means is the idea behind this is that, well, if the gradient, these steps earlier is over there, and I'm adding newest minus my old gradient. So that's the distance, right? That is a distance between my newest and my old. Plus the old. Basically says, well, this is how much progress I just made doing these steps. Okay? And I'm assuming other workers, they all made the similar progress within these steps. Basically, the idea is that, well, we are training like all these workers, we are training the same, training the same set of weights with the similar ground truth. All these gradients, they should make progress in a similar pace. Does that make sense? I have 1,000 workers. They are doing data parallelism. Each of them has their own ground truth, right? Does that make sense? So the gradient should be along the similar pace. Does that make sense? Therefore, basically says, well, I don't know what kind of progress you guys made so far, but I'm just assuming that you guys are making the similar progress as I did. Okay, so this is what you had, and this is the progress I made, and I'm just assuming the progress that I made is the same as the progress you guys made. I'm just going to add that into your stale gradient. So we are making that assumption here. Okay, and by doing this, then I kind of get, you know, the weight that the gradient from you guys. Even I got a stale gradient, but I'm just assuming you guys made the similar progress as I did during these steps. Make sense? Okay. So so that's kind of the idea, but also the mathematical why like this even work. So this two basically is just what I explained, okay? But mathematically we can also like prove that it's a great idea, basically. Why? So mathematically we wanted the true global average at the current time, right? However, we don't have it. We only have the gradient like these steps earlier. According to the Taylor expansion, we can estimate the current value using the past value plus the velocity of the gradient, basically. Okay. Okay. But apparently we do not know the velocity of the gradient. We do know the delay, but we don't know the velocity of the gradient. So we approximate the current gradient with the still gradient plus the velocity times the delay. So this DGA paper like makes this assumption that velocity of the gradient, velocity of the global gradient can be approximated by the velocity of my local gradient, which is about the same speed basically. So basically, if you, and then my velocity is the Wij minus Wi minus dj, right? That's progress I made divided by the d step. That's my speed of gradient change, okay? And when you plug this velocity into this equation, and the d cancels out. So basically, we are using my change to approximate other people's change and to approximate other people's current gradient. Okay, so you plug this, the estimated global gradient now is this essentially. Okay, so that's the whole idea behind this approximation. And it works. So this DGA give you, see where's the accuracy. So this is the speed up. So you can see that's the, where does it compare with the non, well, let's take a look at this one first. So this one, like, come back to this, so basically says, well, without the correction, that's the accuracy. With the correction, you can see 98, 98, I'm sorry, 89, 89, 89, 88.7. Without correction, you can see when you have more and more steps, the accuracy, you can see obvious drop of the accuracy. Okay. So that's that. Real world benchmark, 8 nodes to speed up for vision for language. And that's how many, speed up you can get. Okay. So summarize. In today's class, we talk about how to automate the parallelization. We talk about this output work that's trying to automate the pipelining, the intra and inter parallelization. We talk about bandwidth and latency. We talk about improve the bandwidth. We have a gradient pruning and gradient quantization. For improve the latency, we can't really fix the latency, but we can somehow overcome the latency bottleneck by overlapping and doing this still gradient estimation, right? So, and that we can perfectly hiding the latency. Okay. All right. So that's all. Here's this reference of all the papers we just talked about. Okay. All right. That's all I want to talk about for today's class. So we have one more lecture about on-device training. Okay. And then it will be the final presentation for you guys. Okay. All right. So that's all. Thank you very much.